Hi and welcome to this video. So these are video notes to go through, which I hope you'll follow along and write things in as I write them. And then there will also be a worksheet that follows this and probably a mastery check in class. So if you haven't done already, you should check out a wonderful website here called graphtsandtracks.com. And that's where I did a screenshot here of this. And just before I go and check out graphtsandtracks.com, let's analyze the situation and see if we can answer a couple of questions. It says, what is the ball's initial velocity? So that would be right over there. The ball's initial velocity is set at 10 meters per second. I could also ask, what's the ball's initial position? And you can see by two ways. One is because that's been selected, and also the ball is right over top of that spot. So what's going to happen during A and during B and during C? So during A, well, we're getting pretty advanced in our ability to describe motion, but let's just keep it real simple. During A, it speeds up. During B, it slows down, because it's going to be going uphill, right? And what about during section C, when it's going through that section? It will be going at a constant velocity. You may notice, yeah, I use the word speed, twice or reference it, and then I use velocity. I'm kind of switching back and forth, but I think that's often what we do. All right, now let's go check out this actual website here. So just if I pop over there and I click on practice, then I can set things the way I want them. So you'll see this is the way it starts, but I need to make it look more like the picture that we have there. So this one has to start at 6 high, and then it's 0, and then I think this one goes up to 2, and this one goes up to 4. You can do this as well if you would like to go to this website and try it out. It works on your phone as well. And then the last one is 6. Oh, come on. All right, so now I click on roll the ball, and you can see, ooh, it speeds up. And at the very end, it kind of goes like that. So that's the shape of our graph. It only goes for about 10 seconds. So if I go back over here and it says sketch the position time graph, it's unfortunate, but it's only really going to go for about 10 seconds. So it's not as wide as that. Did I do everything right? Oh, actually, I realized I made a mistake, and I started with initial velocity of 30. So I'm going to try that again and switch to 10. Actually, this is a good little teachable moment here. So what's going to happen to the graph? Well, the beginning part here is going to be less steep, and the whole thing is going to take longer. So I'm going to click on 10, and we'll try it one more time. Oh, it goes really slow at the end. Okay, so that's what it looks like. So let's go over here. And can you sketch that in? All right, so I have the ability to do a little cut and paste, but if you would like to, please, sketch this curve out yourself. And I guess a couple of good points to look at would be that the fact that it hits constant velocity. By the time it gets a straight line, that looks like, to me, like around time equals 7. And it starts off not perfectly horizontal. It actually starts with a little bit of an upslope, and fairly quickly changes its direction with its curve. So here it looks like a bit of an upwards parabola, and now here it's a bit of a downwards parabola. In fact, we can also do a velocity time graph. So here is the velocity time graph. So if I click back to Graphs and Tracks and click on velocity, I have to roll the ball again. So this also gives me some good clues of what's going on here. So it looks to me like it's just about 3 seconds before the velocity changes, and so on. So you can actually also sketch this velocity time graph in. All right, now so I've plopped that one in there as well, and a couple things. You can see like this velocity changes at about 2 seconds or so, so that maybe I'll put 2 seconds right there. And then, yeah, this is about our 7-second mark where it goes at a constant velocity. So here you can see the velocity increasing. That's our speeding up period. And then here it slows down, and then here it's going at a constant velocity. So you see the actual ball moving when you press roll, and you see the position time graph, and you see the velocity time graph. Okay, so let's start with the next section here where it says the definition of velocity. So just a reminder, how did we define velocity? Well, we said velocity was equal to the slope on a position time graph. So if we were to do that more mathematically, we could say the velocity equals, well, the rise, usually I would use position for x for when it's a horizontal motion. So, and here this is time over here. So I would say velocity is the rise, which is the change in x, divided by the run, which is the change in time. Now, what I'm going to point out is that even though there are different kinds of velocity, or different flavors of velocity, you could say, this same formula works for all of them. So the simplest one is the constant velocity. So if I was to put, like, call this one segment A and this segment B and this segment C, where is their constant velocity? Well, that's during segment C. So why don't we try to figure out from the position time graph, what is that constant velocity? Well, we would have to go and say, okay, so, what is this? What's the time and the position for each of those? Okay, so this is clearly 7 seconds. We already figured that out. And say, is it pretty close to about 400? Let's call that one 400 meters. And then what about at the end here? This finishes here, I'd say about 17 seconds. 16, 17. Call it 17 seconds. And the position at the end is going to be about 500. So we can say here for constant velocity, how much did it rise? Well, it rose from 400 to 500. So the change in position was the second one minus the first one, which is equal to 100 meters. How much time went by? What was the change in time? Well, it was at 17 seconds and at the end, and 7 seconds at the beginning, so it was 10 seconds. So what was the velocity? 100 divided by 10. 10 meters per second. Okay, that's kind of cool. Let's go check out over here if that was pretty much what our velocity time graph said. So constant velocity, so this is about 10. Yeah, it seems to be about right. So during the first part, we used our v equals delta x over delta t for constant velocity, and we figured out that it was 10 meters per second. Well, now what about average velocity? For that, for segment C, which we just looked at, that last section, the average velocity was the same. It's if it's not changing, if it's constant, so clearly it'll be the same. But what about during the first section? Why don't we combine together segment A and B? In other words, why don't we start here and end over there at time equals 7 and say what was the average velocity during that period of time? So again, it's going to be the same formula. What was the change in position and the change in time? So the rise section, that would be, let's see if I can draw this nicely, between here and here. So this is the rise. That is the delta x, and that would be equal to 400 meters. And how much time went by? Well, from 0 to 7 seconds, so it would be 7 seconds. 400 divided by 7 doesn't work out perfectly, but it's pretty close to 57. Oh, you know what? I've been putting meters, but I think the scale on that software is actually, it's centimeters per second. So I'm going to say centimeters per second. So 57 centimeters per second. Another way you can look at this is you can say, okay, so the average velocity from here to here, I can also just say, I can say this line here, which I just drew, the slope of that line is equal to 57 centimeters per second. I can kind of sort of turn it into an example of what would look like if it was going constant velocity. So that green line that I drew would be, instead of having the position time graph be all curvy, say, well, if it was going at a constant velocity the whole time, it would have started here, it would have ended over there, and so therefore the slope of that line, which is exactly what we did, 400 divided by 7. Okay, so we covered constant velocity, we covered average velocity. The last one we're going to talk about is instantaneous velocity. And here I've already printed for you a beautiful version of the same graph. At any point along the way, if we are just to stop somewhere and say, what's the slope at that point? It's kind of hard to figure out because it's always changing. But if I want to say, what is the slope? The thing that we do is we draw a tangent. And a tangent will, by definition, cross this at only that point and will have the same slope. The tangent will have the same slope as the curve does at that point. So it's a little bit hard to draw. So if it were it's possible for us to get software to do it for us, then it's a bit better. How about let's put our definition. It's also the rise over the run of a tangent drawn by us or by the computer. So let's see, how about, what is the instantaneous velocity at time equals 5 seconds? Let's see if we can figure that out. Okay, so at time equals 5 seconds, let's see if I can line this up nicely. So if I sort of go vertically, that's the point about right there. And now I have to draw a tangent. See how I do here. I'm going to pick a line and just draw the line. You know, it's not that great. What I can do is I can play around with this line a little bit until I get it so it looks like it's about parallel with that one, and I'll try to line it right over top here. For you, you'd be using a ruler. How's that one look? Does it look like it's got about the right amount of slope to it? Is the slope of the green line the same as the slope of the orange line at that point? I think it's pretty close. Okay, so you would probably want to do this with a ruler rather than, you know, because you can't do it on the software. The other thing I'm going to try to do here is extend the line, just because it gets easier to find points if I make it really large. Okay, so we'll go like that. Okay, so now we're going to look at that tangent and we're going to say, what is the slope of that tangent? So this point over here, where would that be? Maybe 120, and clearly the time is 0. The top point here, this looks like about 500 centimeters. And what would the time be at the top there? If I go down, I would say probably around 7 or 8 seconds. Maybe I'll say 7 seconds, a little bit tough to judge. So how would we figure that out? Well, let's go over here. We're going to say this velocity, again, is going to be delta x over delta t. How much did the position rise? The position rose from 120 to 500, so it's going to be 500 minus 120. How much time went by? Well, that's a little bit easier because it started from 0 and went to 7, so I'm going to say 7. These units were centimeters and this was seconds. So when I subtract that out, I get, what is that, 380 centimeters divided by 7 seconds. I think I'll get my calculator out, and it says 54 centimeters per second. Well, that's pretty cool. So that's the 3 types of position, or 3 types of velocity. This last one's instantaneous. This last exercise we did, finding the instantaneous velocity, gives us a little bit of insight into how you could make a velocity versus time graph. If you figured out the instantaneous velocity at all these points and then graphed it, you would get this velocity time graph. So let's see how we did. So at 5, I'm really going to have to zoom in here. At 5, if I go here, it hits about that spot, and it does look pretty close to our 50. Maybe it was like 45 or something. So it's a little bit tough to draw these things perfectly. So hopefully that works for you for velocity. The next little bit of a topic here is average acceleration. So just a reminder, our definition of acceleration over here was the slope on a VT graph. So the rise over run on the VT graph, instead of being the change in position now, it's going to be the change in velocity. So given that the instantaneous velocity at time equals 0 was 10 centimeters per second, and time equals 5, well, let's go with 50 centimeters per second. Let's keep it kind of easy. Find the average acceleration. So the acceleration is going to be equal to the change in the velocity divided by the change in time. How much did our velocity change by? Well, change is always the second one minus the first one, so 50 minus 10. Because it ended up being at 50 centimeters per second, it started at 10. How much time went by? 5 seconds. So we have a change of 40 centimeters per second over a period of 5 seconds. 40 divided by 5 is 8, so we get 8 centimeters per second per second. We can also say 8 centimeters per second squared. I kind of like this one in a way because it says for every second that goes by, the velocity is going to change by 8 centimeters per second. Turning to the next page, I set up a question that will be very similar to the worksheet that you're going to be doing. So here is a velocity time graph. So just imagine what this looks like. The object starts with a positive velocity of 3 meters per second. It gets closer to 0. It actually stops right there. And then it increases in a negative direction. So it says give a written description of the motion. So I'm going to say here it starts moving in a positive direction. Then it slows down. Slows to a stop, actually. And that's at 2 seconds. I'll do bullets here, just keep track of things. And then after that, at this point, now it speeds up in a negative direction. So really between moving in a positive direction and moving in a negative direction, so just to point this out, it changes direction. Okay, so sketch a motion map, and we're going to include velocity and acceleration vectors. So let's start off and say, well, do we know where it starts at? We don't, do we? Because it's starting at 3 meters per second, but we don't know what position it's starting at. It's going to be going in the positive direction for a little while, and then it's going to mostly be going in the negative direction. So overall, its motion is going to be in the negative direction. So instead of starting out, I'm just going to erase that. Instead of starting out at the origin, I'm going to start off way in the positive place over here. So this is going to be my start here, and it's moving in the positive direction a little bit, and then it changes direction and goes in the opposite direction. So I'm going to have it change direction and then move more quickly. So there was a jump of 1. There, I'm going to not put too much effort into this, but I'm going to put this initial velocity is going this direction there. This is where it stops. This is where it's going in the other direction, going in the other direction, and then at the end it's still moving really quickly that way. So these are my velocity vectors. Okay, and I'm also going to mention that this is the start. Did I put enough dots? T equals 0 in it. So it seems to me that each dot is happening every 2 seconds the way I did this, because if this was 0, that would be 2, 4, 6. Yeah, I think I did this with not very many dots. So each dot represents an elapsed time of 2 seconds. That would be the start. This would be the end. Okay, so now how would I figure out the acceleration? Well, first I'll put the same dots down here just to make it a little bit easier. How did the velocity change? I better pick I'm going to go with green on this one. So between the first dot and the second dot, I went from a right arrow to no arrow at all. So the change was to the left. So I'm going to make this change to the left. From this dot to that dot, I went and put some left into it. So it's the changes to the left. These are the acceleration, is how the velocity is changing. And again, this would be the entire time is to the left. A good clue, if you're not sure about this, I'll just put A all along here, is, well, what is acceleration? It's the slope. And this is a downhill. So A equals slope. And clearly it's a constant negative slope. So my A arrows, my acceleration arrows, should go to the negative direction and should all be about the same length. So you see it starts here, it moves forward a little bit, and then reverses direction, and you can see it speeding up to the left. It says determine the displacement from 0 to 2 seconds. Okay, so this is the big thing here, displacement on a VT graph. So displacement, the change in position, is equal to the area on a VT graph. So if I want to go from 0 to 2 seconds, then I'm talking about this area right there in nice beautiful yellow. So this is above the line. This is a positive velocity. So in other words, this area is going to be positive. So I would say this shape, if I'm going over here, this delta x is going to be equal to, since it's a triangle, it's 1/2 times the base times the height. I think that's too thick. So what is 1/2 the base? Looking at that triangle, the base is 2 seconds, so I'm going to say 1/2 times 2 seconds times the height, which is 3 meters per second. What's 1/2 times 2? That's just equal to 1. 1 times 3 is 3, so I get 3. Check out what happens to my units. My seconds cancel each other out, so I get 3 meters. How far did it move? 3 meters. Not bad. Okay, determine the displacement from 4 to 8 seconds. From 4 to 8 seconds, okay. So that would be this area here. That's a tough shape to do, isn't it? Maybe I'll do my work over here. So to do that shape, well, there's two methods here. Number one method is to say, because we have to figure out this area, we can call this a rectangle. Area is equal to a rectangle plus the triangle underneath it. Okay, and I think this is probably how most of you would solve this problem. So the area of the rectangle, well, this goes from 4 to 8, so that's going to be, this distance here is going to be 4 seconds, times, this is minus 3 meters per second. So one thing we'll notice is that this area, the blue area altogether, is going to be negative displacement because they're moving in a negative direction. Plus, now the triangle part is going to be 1/2 times the base times the height. The base is also 4 seconds, and the height of the triangle here is minus 6 meters per second. Okay, so that's kind of a weird one. Because it's below the line, it's negative. 4 times negative 3 is negative 12 meters. So this area here is negative 12 meters. And then this area here is, let's see, 1/2 times 4 is 2. 2 times 6 is also minus 12. So this area is the same. And so we get minus 24 meters. So here, I'll just put that work over here, minus 24 meters. The second way you could do this is you could, method number 2, this is a little bit fancy, is that shape is known as a trapezoid. Depending on which country you learned your geometry, it could also be called a trapezium, a little bit more British. I think in Canada we usually say trapezoid. So how does the area of a trapezoid look? Well, a trapezoid is something that has two parallel lines. And if you want to figure out the area between them, we take the average of the bases, b1, b2, and multiply by the height. So the area would be equal to the average of the bases, b1 plus b2 over 2, multiplied by the height. So this trapezoid, let's see if I can erase just the red lines. No, it didn't do very well. Okay, I'll just draw it in again. Bear with me. So this is between 4 and 8. Okay, so this trapezoid is kind of laying on its side. It's not really the way we'd normally look at it. So let's see. Coloring's kind of fun. So let's see. This we could call base 2, this length here, and this would be base 1. So over here we could say base 1, which is 3 meters per second, and this base, which is minus 9 meters per second, or 9 meters per second. I think what I'm going to do is just find the area and then at the end just call it negative. It might be easier than, doing minus 3 and minus 9. Divided by 2, so the average of those two, and then multiplied by the height. So the height in this case is going to be our 4 seconds. 3 plus 9 is 12. 12 divided by 2 is equal to 6, so we get 6 meters per second multiplied by 4 seconds. So again, hey, isn't that cool? I get 24 meters, and then I remind myself, oh yeah, but it's all below the line, so it's going to be negative. You could do that same method about not putting in the negatives right away. Like over here, I put the negatives in the beginning. You could just leave everything as positive and then look at it and say, oh, but it's below the line, so it's going to be negative. So in any case, our answer for that one is minus 24 meters. It says, determine the average acceleration of the object's motion. Okay, so again, what is acceleration? Acceleration is equal to the slope on a VT graph. When we're talking about average acceleration, well, we'd say, what was the velocity at the very beginning? The velocity at the very beginning was 3. At the end, it's minus 9. So how much did it change by? Well, it went down by 12. So the change in velocity was minus 12 meters per second. What was the change in time? How much time went by? 8 seconds. So negative 12 divided by 8, what is that? 1.5, 1.5 minus meters per second. Or if you want to, you can write meters per second squared. So for every second that goes by, on average, the velocity reduced by negative 1.5. Here the last question says, sketch a possible position time graph for the motion of the object and then explain why your graph is only one of many possible graphs. Well, it's just like when we made our motion map, we weren't sure where to start. So we started way off over here in the positive zone because, I said, because we're only going in the positive direction for a little while and we're mostly going in the negative direction. So just to fit it onto our motion map, we started way over there. But it's indicating the fact that on a velocity time graph, it doesn't tell you where you start. There's nothing on here that says what your position is. So explain why your graph, let's do that one first. We'll say a VT graph doesn't tell us starting position. Starting position, x naught, x0. So how about for this one, if we do this one, let's start at our origin. Let's try it out. So we've got, 8 seconds. So here's 4, here's 8, 2, and then 6. It's going to be moving in the positive direction. After 2 seconds, we found out it goes 3 meters. So if we're thinking about all these units here, this section here is going to be plus 3 meters. This clearly is the same shape, it's just below, so it's going to be minus 3 meters. And then this shape over here, we found in 2 different ways, was minus 24 meters. So overall, it's going to move forward 3 meters, and then it's going to be moving back 3 meters and end up at the origin again, and then it's going to go minus 24. So when we're going in the minus section, this will be minus 24 over here. So and this would be, I don't know, 3 right there, something like that. So it starts off moving quickly. So the beginning velocity is 3 meters per second. So in other words, it starts going up like this. At 2 seconds is where it stops, so that looks horizontal. At 4 seconds, it's gone -3. So I'm trying to do better here. Let's zoom in. So at 4 seconds, it kind of goes like this, right? And by the time, and it gets steeper and steeper, and by the time it gets to 8, it is at 24. So that would line up, that 8 with the 24. So it's got a nice little kind of a parabola curve there. I'm trying to make it curve. Maybe the last bit of my line looks like it's straight, so I should try to do a little bit better to say, oh yeah, this is still curving downwards a bit. So a little bit of a curve. That entire curve, you can see, looks like part of a nice parabola, although it's just sort of cut off right over there. Okay, so I hope that helps. Now that you've gone through this sheet, please do the same worksheet, the worksheet that has that same name, Interpreting Graphs of Accelerated Motion. And as always, I look forward to seeing you in class.